Now, class number 11, derivatives from the IB Mathematics standard level course we are covering. Derivatives. Let's start with derivatives. Let's say I'm having a line. This line is drawn in green. And I want to find the gradient of this line. Simply to find the gradient of this line, I need the change in y over change in x. This is clear, simple, and easy. But suppose we have this type of function. Let's draw our axis first. Suppose I'm having this quadratic function and I want to find the gradient, let's say at this point. So, in order to find the gradient at this point, I need to draw a tangent to the curve at this point. This is the tangent. This is in the red, is a tangent. And I need to find the gradient of this tangent by having 2 points, which is change in y and change in x. So, for a function which is concave, is not a straight line, to find the gradient at any point, I need to find the gradient of that tangent at that point. So I have to draw the tangent. I get 2 points and I get change in y over change in x. I can find the gradient of that tangent. But drawing that tangent, I may not have accurate results. Plus, if I need to know the gradient at any point, let's say I want to find it at this point, it's not logical to keep drawing tangents to find that gradient. So that's why I need to derive. I need the first derivative of the function The first derivative is the gradient function of the tangent. By finding the first derivative, I can find the gradient of the tangent, and it's so important to know that it's of the tangent at any point on the curve. That's why we derive. Let's say this function is f of x. The first derivative, if it's f of x, or this function is represented by y, the first derivative here is f prime of x, or if it's y, the first derivative would be dy over dx. This is what we have to know about the first derivative and why we do derive. So, if I'm having a function, f of x, which is equal to x to the power of n. I'm having f of x, which is x to the power of n. And I need to find the first derivative of x. I get, now, to find the first derivative, I get the n down in here, and I subtract 1 from the n. So the first derivative becomes n times x to the power of n minus 1. This is how we derive. We have many rules when it comes to derivation. The first rule is the product rule. The product rule, let's say I'm having f of x is equal u of x times v of x. And I want to find the derivative of f(x). This is called the product rule, when I have two functions multiplied by each other. So when I want to derive this, I need u prime of x multiplied by v of x plus u of x multiplied by v prime of x, which is the first derivative of the first function times the second function plus the first function times the first derivative of the second function. This is the product rule. Let's go to the quotient rule. Is when I have two functions divided by each other. The quotient rule, let's say I'm having f of x is equal to u of x over v of x. The function u of x is divided by the function v of x. So to find here f of prime of x, this is equal to v of x times u prime of x minus v prime of x times u of x, all of it divided by the function in the denominator squared, v of x, all of it squared. This is the quotient rule. I hope it's clear till now. Now, if I'm having a composite function and I want to derive it, I use the chain rule. The chain rule, what does it say? Let's say I'm having f of x equal to v of u of x. And I want to find the first derivative or to derive this function. So first I derive the outer function. So I say v prime of u of x multiplied the derivative of the function inside the bracket, u prime of x. This is my chain rule. This is my chain rule. Now, let's talk about v. For a function, let's talk about turning points and the second thing we have to talk is the inflection points. Turning points, when I want to find the local maximum of the function or local minimum. I have a turning point when there is a change in gradient. So, I've said I find the gradient of the tangent at any point using the first derivative. Change in sign for gradient. So here I need to use the first derivative. This is to find turning points. To find inflection points, it is where I'm having change in concavity. I'm having change in concavity. Where is there change in concavity? I need change of sign of the second derivative. So in order to find concavity, I need the second derivative. To distinguish between turning points and inflection points is really important. To distinguish between turning points and inflection points is really important. Let's have an example. If I'm having f of x is equal to x cubed minus x squared minus x minus 1. And here I need to find the turning points and the points of inflection. If I want to see the behavior of this function or how it's sketched, I can use my GDC. So I start my GDC, I go to y equal, I want x is x cubed minus x squared minus x minus 1. And I go to graph. This is my graph. Let me just decrease the boundaries of the window. Let's go to window. X minimum, let's make it minus 3. And the X max, let's make it 3. And we go down to Y minimum, let's make it minus 5. And the Y max, let's make it 5. So graph. This is my sketch. If I want to find the local max and the local minimum, I go to second calc. I'm having a minimum here. I want the left bound of the minimum. It's this way. And the right bound, I go to the right. I'm sorry. I go to the right. Enter. And I want the expected value to be here because it's my minimum. And I press enter again. So I'm having a minimum at x equal 1 and y equal to minus 2. This is my minimum value. This is my minimum. To find the max, I go second calc. I go down and I want the max. Where is the left bound? I go to the left bound. It's fine. I have to keep going till I go to the left of the maximum point. And I want the right bound, which is here. I press enter and I go to expected value, which is in the middle of my 2 points. And I'm having a maximum at x equals minus 1 over 3 with y minus 0.8148. These are my minimum and maximum values. So I know the shape of the function. In order, I can draw it here now. Let's draw. My function is like this. Something like this. So, if I want to find the gradient at the maximum point, I need to draw a tangent here. I need to draw a tangent. This is my tangent. The gradient of the tangent is equal to 0. And at the minimum point, also the gradient of the tangent is equal to 0. So, the first thing to do to find the local maximum and the local minimum, which are the turning points, I need to find the first derivative and equate it with the 0. So let's derive our function. So f prime of x is equal to 3x squared minus 2x minus 1. And I need to equate this equation with the 0 to find the turning points. Let's start. This is 3x squared. I'm going to need 3x squared minus 2x minus 1 is equal to 0. I need to find the x's that makes my equation 0 and plot it on the number line. On this number line, I'll tell you why. In order to solve this equation, if it can't be factorized or it can be factorized, we go to apps. We go to our GDC again. Second quit. We want to go to apps. Second quit. I'm sorry. If you can see, this apps is not working here on my GDC. The reason why is maybe on the application does not have the full applications because of the software. But for your GDC, you'll have the full applications. Okay, in the case we don't have the apps, we can sketch our function and equate it to 0. We go again to y equal, let's clear this. I need 3x squared minus 2x minus 1. Let's graph it. I'm having this graph. And I need when this function is equal to 0, so I go to second calc, this 0. My GDC asked for the left bound. This is my left bound. My right bound. This is my right bound. And the guess, this is my 0. At minus 1 over 3. The first 0 is minus 1 over 3. So here I'm having a minus 1 over 3. And the second 0, second calc, I need to find the 0, which is number 2. The GDC asks for the left bound. This is my left bound. And the right bound. This is my right bound. And the guess is in between them. So the second 0 is at x equal to 1. This is at x equal to 1. And I need to find the sign of the function before the minus 1 over 3, between the minus 1 over 3 and the 1, and after the 1. If I can see my GDC, the function before the minus 1 over 3 is positive. And between the minus 1 over 3 and the 1, we can see it below the x-axis, so it's negative. And after the 1, it's positive. So, the gradient for my function before the minus 1 over 3 was positive. This is positive. I'm sorry. Just, erase it. The gradient is positive, which is increasing. Then, at minus 1 over 3, it becomes a 0. Then a negative, decreasing. And at 1, becomes a 0 again. And after the 1, it's positive. So, at the minus 1 over 3, I have a local max. At the 1, I'm having a local minimum. That's exactly what we had on our first sketch. This is exactly what we had on our first sketch. Then, the second thing is we need to find our inflection point. Inflection point, I find it when I equate the second derivative with the 0. Inflection point when I'm having a change in concavity. It must be here, because if we can split our function, we can find that here we have it concaved down, and at this part we have it concaved up. But we need to find the x value for this concavity. We need to find the x value for this concavity. So for the inflection point, we need to find the second derivative. So now, f double prime of x is equal to 6x minus 2. And when I equate it to 0, I'm having a 6x minus 2 is equal to 0. So I'm having a value the value of x is equal to 2 over 6, which is x is equal to 1 over 3. I'm having an inflection point at x equals 1 over 3. Let's check if this inflection point is valid, because I need also to have a change of sign before the 1 over 3 and after the 1 over 3. This is the 0, 1 over 3. Let's see the sign before the 1 over 3 and after the 1 over 3. We can sketch it over our GDC again. We go to y. Let's clear it. I need to sketch 6x minus 2. 6x minus 2. And I graph it. The 6x minus 2, you can realize that before the 1 over 3 it was a negative. And after the 1 over 3, it's a positive. So, before the 1 over 3, I'm having a negative value. And after the 1 over 3, positive. And be careful. In the second derivative, the signs represent the inflection or concavity. It represents the concavity. If we can see that before the 1 over 3, it's negative, which means the function is concaved down. And after the 1 over 3 is positive, which means the function is concaved up. In the second derivative, the signs represent concavity. So as we can see in our graph, the function starts by being concave down, then it's concaving up. At what x value? At the x equals 1/3, I'm having a change in concavity. So, for differential calculus, it's essential to know what's meant by the first derivative, by the second derivative, what do they represent, how to find the derivative using product rule, using quotient rule, and using the chain rule if we have composite functions. This knowledge is really important. So now let's go to solve a question from the question bank as well. The following diagram shows the graph of f prime of x, the derivative of f. This shows the gradient function of the tangent, which is the first derivative. This function drawn gives me the gradient at any point of the function. I don't have the function f drawn in front of me. So now, the graph is given in the question. The graph of f prime has a local minimum at A. Here is a f prime, local minimum at A, which means that I'm having a change in concavity here, and the local max at B passing through 4 and -2. The point P has the coordinates 4 with 3, lies on the graph of F. So the point P is on the original function. Part A, I write down the gradient of the curve of F at P. At the point P, what's the x coordinate of the point P? Is 4. The x coordinate of the point P is 4. I need the gradient, which means the gradient I need is f prime of 4, which is the y value at the 4 here. F prime of 4 is equal to -2. Because when x is equal to 4, on this graph, the y is equal to -2. I, find the equation of the normal to the curve of f at P. I need to find the equation of the normal at P. Equation of the normal, I'm having the gradient of the tangent to be, the gradient of the tangent is equal to -2. So to find the gradient of the normal, I need to change the sign and flip this value. So it's +1/2. This is my gradient of the normal. And as we discussed before, to find the equation of the normal, which is a line, I need a point which is 4/3, and I need a gradient, and I can find my equation of the line. So my equation of the line is y - 3 is equal to half times x - 4. This is the equation of the normal. No need to expand it. By reaching this value, I can get full marks. Part B, determine the concavity of the graph of f when x is between 4 and 5, and justify your answer. Okay. To determine the concavity, we've said to determine the concavity, we need f double prime of x. To determine the concavity, we need f double prime of x. So we need to draw the derivative of f prime of x to find f double prime of x. As we can see, from the first segment till the point A, I'm having a negative gradient. And from A to B, I'm having a positive gradient. And after B, I'm having a negative gradient again. So to draw my second derivative function, here I'm having a negative gradient, so this is negative. It's below the x-axis. And then I'm having a positive gradient, and here I'm having an inflection point. So it will flip at this point. I'm having a positive gradient, so above the x-axis, till B I'm having a positive gradient, and here I'm going down again. The concavity, as we discussed in our example, is represented by the sign of the second derivative. So from 4 to 5, I want this area. From 4 to 5, I want this area from here to here. If I can see, the sign of the second derivative from 4 to 5 is positive. So part B, I'm having a positive concavity. Part B, I'm having a positive concavity. The reason why I'm having positive concavity, because the second derivative is positive from 4x to the 5. The second derivative is positive for the values of x that lies between the 4 and the 5. As always, what I say at the end of each class, always do practice, 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 and practice.